So we've been talking about radioactive decay, and the question is why do nuclei decay? And a better question might be why do they stay together at all? Because if you think what a nucleus is made up of, it has a bunch of protons in it. So we're going to make a note that nuclei are made up of protons. So there's a whole bunch of positive charges right near each other. They should repel. So scientists decided that inside the nucleus, there is a force stronger than the electrical repulsion holding the nucleus together. So they gave this force the name, the strong force. Okay. So what we know about it is stronger so it's very strong. It's stronger than the electrical force. But it only acts over a very short distance. About the size of a nucleus. So science come up with the idea that there are four fundamental forces, and the four fundamental forces make up all of the forces in nature. And the four of them are gravity, the electromagnetic force, the strong force, and a force that's called the weak force. So, for example, when I push down on a desk, the desk pushes back up on me. That's actually the electromagnetic repulsion of the protons in my hand with the protons in the desk. So here's a chart showing the different forces and their strength. The weak force actually isn't the weakest. Gravity is actually weaker than the weak force. The reason we don't feel the weak force is it's very short, only acts inside the nucleus, 10 to the minus 18. The strong force is the strongest, but it also only acts over a very short distance, 10 to the minus 15. And that actually puts a limit on the size of the nucleus. If you think about it, there's only about 100 different types of atoms. So if you look at the periodic table, the biggest has an atomic number of around 100. It's because if you start to make nuclei that are bigger than that, you end up with a nucleus that's bigger than 10 to the minus 15th meters. The strong force doesn't work past that, and then the electromagnetic force will make the protons repel. Of these, I'm going to make a note that the strong force is sometimes called the nuclear force. So if you see the word nuclear force, they're talking about the strong force. You don't really need to know much about the weak force. It does exist inside of the nucleus, but we don't see it um, very much. And the gravity and the electromagnetic force reach to infinity. Half-life. Half-life you learned in earth science and you learned in Regents chemistry, so this should be pretty easy for us. It's the time it takes for half of a substance to decay. For radioactive decay, I can't look at any one atom and know when it's going to decay, but I can kind of average it out over time, and I know that about half of it will decay in one half-life. Here's an example. Substance A decays to substance B with a half-life of 2 days. I'm going to start with 100 grams of A, and how much of A and B will I have after 6 days? So I can make a chart like this. I have 100 grams. Okay. And then after one half-life, I'm going to have half of that left, so I'll be down to 50 grams. And that time took 2 days. So each arrow represents one half-life occurring. So then after another half-life, which would be another 2 days, I'd be down to 25 grams. And then after another 2 days, I would be down to 12.5 grams. I just keep dividing it in half. And that takes me up to 6 days, so I've done enough half-lives. So I know I'm going to have 12.5 grams of A left over. Now sometimes they won't ask for how much of A you have left, they'll ask how much B you have. And if I started out with 100 grams and I only have 12.5 A left, to find out how much B I have left, I would have to subtract. And that's going to give me a value of 87.5 grams of B. A doesn't just disappear, it's turning into B. And we have to keep that in mind. Okay, we've been talking so far about natural transmutation, naturally occurring radioactivity. Artificial transmutation is when you hit a nucleus with another nucleus or an alpha particle or a neutron, so we just say a particle, causing it to decay. So I have an example here. I have uranium-235. So uranium, or sorry, 325. And the atomic number for uranium is 92. It's going to be bombarded with neutrons. So I'm going to hit it with a neutron. A neutron has no charge and a mass of 1. And that's going to cause it to split up. And in this case, it says barium-141. And krypton 92. The atomic numbers for these, barium is 56. And the krypton is 36. And then I'm going to have some other stuff over here. So I have to make this balance again. All right, so I have 92 on this side. And if I add 56 and 36, that's going to give me 92 as well, so I don't have to have any charge here. But on this side, I have 326. And on this side, I have 141 and 92. If I add those together, I'm going to get 323. So the difference is 3. So I have something with no charge and a mass of 3. And now it's telling me how many neutrons. I know a neutron is 0 and 1. So how many neutrons would I have to make up to get How many neutrons would I have to get a 0, 3? I would have to have 3 neutrons. Now, a lot of times the question would just be, is this natural or artificial transmutation? If you're hitting it with something, if there's two things on the left, it's going to be artificial. This won't split unless I hit it with that neutron. We're going to finish off with nuclear fission and fusion. Nuclear fission is splitting big atoms into smaller atoms. Okay, so there's energy release in the process. Atomic bombs and nuclear reactors use this. When you split a big atom like uranium or plutonium into smaller ones, you get energy out. Okay. And nuclear fusion is when you take small atoms or small nuclei and combine them to make bigger ones. And again, energy can be released in the process. This is an example for hydrogen bombs and the reaction powering the sun. An example of a fusion reaction would be hydrogen plus another hydrogen makes helium, which is bigger, and then there's a neutron. And that's what's happening on the sun.